5 for the bomb calorimeter with group number 3. I'm the group leader. The group reporter is Eduardo Nunez. 6-minute thermo topic given by Austin Lovell. The table topic for this week was for Stephen. It's an overview of this presentation. Basically, I'm going to give an introduction on the bomb calorimeter, the objectives involved in this experiment, the thermodynamic background in theory, and any explanation of definitions you might need to know, the experimental apparatus used to complete this experiment, the procedure, and any theoretical results that I obtained. Introduction, the PAR oxygen bomb calorimeter is the one used in this experiment. Its definition is kind of wordy. Basically, it measures the heat released by combustion. It's designed to measure heat liberated by combustion of solid and liquid samples in the oxygen bomb. Like I said, basically, resulting from combustion, you measure the heat, and that's what this does. It's also used for analyzing combustion products, and the oxygen type bomb calorimeter is the type we're using, and it's accepted standard for accurate measurement of heats of combustion. The objectives involved in this experiment include becoming familiar with the physical principles, procedures, and the analysis techniques associated with the oxygen bomb calorimeter, determine the thermal capacitance and the gross heat of combustion of the provided samples. The theory behind this experiment, definition for heat of combustion, again it's a little wordy. As determined with this oxygen bomb calorimeter, is defined as the number of heat units liberated by a unit mass of substance when combined with oxygen in an enclosure of constant volume. Basically, how much heat is released from combustion. That's what heat of combustion is. We're going to ignite the bomb calorimeter. Heat is transferred from the internal surface to the surrounding water, and this is done by conduction. And we observe the rise in water temperature, and from this we can calculate our Q value, or our number of heat units liberated, or heat of combustion. Here's a little image basically of a bomb calorimeter. Basically at the bottom you can see where the combustion is happening and then the temperature is rising. First law of thermodynamics provides the basis for this experiment. Q is equal to mass times specific heat times delta T. Mass times specific heat for constant volume, that's the subscript V, is the thermal capacitance. You rearrange the equation, you can calculate the thermal capacitance. If the calorimeter, everything, like the whole system, everything but the fuel is chosen as your system, and you know what fuel you're burning, you know your value for Q. And from this, then you can calculate your thermal capacitance from the equation right here. Where Q is the heat of combustion, and mass times specific heat is your thermal capacitance of the system. In this experiment, we also will burn an unknown fuel, and to determine the value for Q, use the equation above. So apparatus, at the top right here, you can see that's your thermocouple. The DAQ is connecting to the computer. It's software that records your temperature measurements. The bomb is in the middle right here. The next page you'll be able to see it more in depth. Basically that's your water jacket, your bomb goes in your water. This is a close-up of the bomb calorimeter. You got your check and release valves, you know, to keep your bomb from getting over-pressurized and possibly exploding. You can see all of this in the lab manual as well. The procedure, it's detailed in the lab manual. I just want to run through a few things. Basically cut 10 centimeters of wire. You know your fuel initially is the benzoic acid, which we know our heating value for. We place that in the bomb calorimeter. You connect all the ignition wires, you add some water. You want to screw your lid on. You don't want to overpressurize your lid, your bomb. You want to leave it at 30 atmosphere because it can be dangerous, it can explode. You add your water, place the bucket down in there, start your computer, start your software, insert your thermocouple, start your recording data. When you record, you always want to get baseline data first. That's what any experiment in general will do in here. You want baseline data, and then you ignite the bomb, and then you'll see a jump in temperature. From this jump in temperature, we can calculate our thermal capacitance as well as when we conduct the experiment with our unknown fuel, we can use that to determine our heat of combustion. Theoretical results I obtained, the capacitance, the thermal capacitance, there's the CV values for your system. I got these online. For water and steel, you add these together to get the value for your system. The Q value for our fuel is listed as 6,318 calories per gram. I made an error in my calculations, or I obtained the wrong figures online because I got my delta T as 5,743 kelvin. Obviously, that's way too high, so I have to go back and figure out exactly what went wrong. In uncertainty in this experiment, it's anything basically, human errors obviously in uncertainty in any experiment. Uncertainty in your type K thermocouple, as well as any uncertainties in the measurements of fuel that you use to burn and the amount of water. If you mess up on any of those, your calculations could be a little bit off. Are there any questions? All right, thank you.